Good afternoon, everyone. Starting with a few announcements. So I posted an announcement on Canvas yesterday, actually two announcements. One was about Homework 01, the other one was about the app called Gradescope. Um, let's talk about the homework first, then I will talk about Gradescope. So let's do this and go to our Canvas website. So homework 1 is currently due on Sunday, but I like to give at least a week. We're going to cover most of the example topics of homework 1 today in class. So you have sufficient time to get it done by Sunday night. But as I said, I like to give a entire week for the homework assignment. And so I will accept submissions until Wednesday. Canvas will show a due date of Sunday, but submissions will be accepted until Wednesday. Okay, and I posted that in the announcement. So if you have not yet had a glance at the announcements, that's what it's in there. Sometimes I used emails for like quick communication, but some important stuff I might send an email and post an announcement. But typically everything will be posted on an announcement, so all the information is there in one place, and you don't have to go searching through emails. So anytime a notification pops up in your email inbox, please open up the messages and read the announcements. Okay. If it doesn't pop up, a notification doesn't pop up, then you need to go into the Canvas settings and you need to enable notifications for your email as well as your phone app. Okay. So it should pop up on there. All right. Gradescope. This is one of the reasons why I was delayed by a few days. So Gradescope is an app that allows us to do rubrics-based grading, allows us to grade faster and better and more efficiently, also allows us to provide good feedback to the students. Okay, so students can see if they're losing points, where and why are they losing points. Okay, so it gives you feedback in that sense. And so quiz 01, which we already submitted, I have reposted as a Gradescope assignment. Homework 01 is already a Gradescope assignment. Let me go view as a student. And then you can access directly in the assignments tab. So it just shows up here. You have quiz 1, student submission, and you have homework 1. So you can do that. All right, it's a link to a Gradescope assignment, or you can simply open up the Gradescope tab from the left. And then when you click on that course, it'll show you homework 01 and quiz 01. And you go ahead and upload your submissions. And when you upload your submissions, what you will see is this. So let's say quiz 01, for instance, right? In quiz 01, actually, I'm in student view. Sure, that's the grading dashboard. Okay. Because I'm an instructor, it's not simulating a student view in there. So I guess I'm unable to show it to you. But at your end, when you click on there, it'll ask you to upload a PDF or submit an assignment as you would for Canvas. So when you upload it, depending on the instructor and the assignment, depending on the assignment, the instructor, whether it's me or whether it's any of your other classes, will create certain points or regarding the questions. So in our quiz, we had 10 questions. And so in your upload, after you're finishing upload, Gradescope will ask you to note down the page where your answer or response is to each specific question. Okay. And there's a video guide link that I embedded in the announcement. So just go through that. It's just a few minutes. All you're doing is basically selecting the page, and then you're selecting, question number 1, 2, 3, 4, 5, 6 is on page number 1. And then you select page number 2, and then 7, 8, 9, 10 is on page number 2, and so on and so forth. And that's all you have to do in addition to the upload. Okay. There's nothing too onerous or time consuming in there. Just takes a few clicks. And then at my end, when I have it and I sit down to grade, I just go click on it, and then I can enter the points and I can enter the reason, and students can see what exactly is going on, right? So Quiz 01, which you already submitted, I'm just asking students to resubmit it again. And I have 3 days for that assignment. Yeah, October 3rd. So 3 days counting from last night. So just upload it again in that spot, right, where it says quiz 01 student submission. Just upload that PDF again, right? Clear to everyone? Okay. All right, so let's leave the student view and go to our notebook. Okay, not that. Let's go to this one. All right. So we stopped here last class, and we were talking about voltage, current, and power. Does anybody have any questions? Any questions at all? Okay. I think we were in a bit of a rush last time, so I'm going to take a few minutes and go over this concept again. Let's see. Okay. All right. So the power equation for electrical power, the equation is simply the product of voltage and current. P equals V times I, voltage times the current. P of T stands for instantaneous power, meaning power at any given point in time. So if we are analyzing a system, whether it's for a few seconds or a few minutes or a few days, doesn't really matter. But at any instant in time, if we are trying to calculate the power, it would be P of T. Power as a function of time, equation still is true. It's V times I. So it's V of T times I of T. Okay, and that's what we have in this equation right here. P of T is V of T times I of T. Now, electrical power, electrical energy comes from the source, and the loads receive or consume that energy. More often than not, in this class, we are talking about resistors, capacitors, and inductors, some diode circuits, but mostly it's resistors, capacitors, and inductors. So let's just talk about resistors for now. Resistors receive energy and power from the source. They dissipate in the form of heat. So electrical energy is converted into thermal energy. There are real life applications, electric heaters, for instance, cooktops, electric cooking ranges, right? Electric current passes through a metal coil. It has some resistance. It opposes the flow of current. When it opposes, it gets heated up. Electrical energy is converted into thermal energy. And so you can now use that heat in a variety of ways. You can use it as a space heater. You can use it as a water heater. You can use it as a cooking device, just to name a few. What other appliance, large or small, can you think of using the same principle? Anyone do laundry? Right? You have electric heaters used in dryers. Also, if you ever ironed clothes, that again is based on the principle of electric heating. All right, so that's the real life applications, right? When we are calculating the power or the energy, we want to balance out our equations mathematically. And so if it's a source, we put a minus sign in front of that equation. And that's it. The P equals minus VI. And if it's a load, P equals plus VI. And I think this is where we had stopped. All right, any questions about anything on this page? Total energy in that process would be the summation of all the power that was transferred within a certain time frame. That means mathematically all we do is we take the area under the curve, slice it up, dt, and then add up all the slices, meaning we integrate from 0 to t. And that's how we get W is equal to integral of t. So energy can be calculated by integrating the power over a certain time period or certain time frame. And that's what this equation is. Have you all seen this in previous physics classes? Right? Again, hopefully it's just a refresher and you remember most of it. Okay, so a switch, electrical switch, is noted with this symbol right here. Okay. Here the switch is open, and here the switch is said to be closed. Open and closed. Okay. When the switch is open, no current can flow through, so I is equal to 0. And because the switch is open, a potential difference could exist at the two ends of that switch. And so voltage could be non-zero. Okay, the voltage could be non-zero. So like a plain electrical switch. Plain electrical switch, if it's open, will not allow current to pass through. The voltage could be non-zero. Conversely, if the switch is closed, or I should rather say, if we want current to flow, then the switch must be closed. So if the switch is closed, both ends of the switch are now connected to each other. If both ends are connected, it provides a pathway for current to flow through. But because it's now a short, no voltage can exist across those two terminals. Right? If two nodes are connected by a wire, or 2 points are connected by a wire, then there is no difference in electrical potential between those 2 points, meaning voltage is equal to 0. So for an ideal switch, if you close an ideal switch, current will flow through, voltage would be exactly equal to 0. And in real life, we always say that there is no ideal component, no ideal conditions. There's always some effect. But in real life, if we turn on like a manual switch, like a light or a fan, it might have some minor resistance, would be in milliohms perhaps. And so a really small fraction of current or voltage might be lost in that switch. But that would be like microamps or nanoamps of current and millivolts or less of voltage. Okay. Yes. Yes. Question being asked is, or basically, does the voltage equal 0 across a closed switch? And the answer is yes. The reason is both nodes are connected together. All right, let's take a pause. Let me know if you have any questions. Yes, so in both cases, so question being asked is about the electrical power for the switch. And so electrical power, again, is the product of voltage and current. And no matter whether it's open or whether it's closed, not at least, out of those two quantities, V and I, one of them is 0. And hence power is equal to 0. Meaning, for an ideal switch, there is no power loss. In a real switch, as I said, we might have some small amount of resistance, so small amount of current loss or voltage loss, so small amount of power that's being lost in there. Probably not even milliwatts, probably microwatts or less. But an ideal switch, the power loss would be equal to 0. And so we say it's a non-energetic device. Okay, non-energetic. To be really colloquial, it's a lazy device. Not really. Non-energetic in this case simply means it's not using up any energy. All right. Okay. Let's go to some example problems after this. All right. So what have we learned so far? Well, ideal resistor based on Ohm's law has the equation that satisfies V equals IR. So for a resistor, the equation is V equals IR. For a inductor, draw out the symbols right here. R. For a inductor, V equals L di over dt, inductor times the time rate derivative of current. And for a capacitor, we write in terms of current. And so I is C dV over dt. And that's for the capacitor, R, L, and C. On a side note, circuits that contain R and L are known as RL circuits. Circuits that contain R and C are known as RC circuits. And circuits that contain all three are known as RLC circuits. Okay. All right. Now we have two equations. We have Ohm's law, V equals IR. And we have power equation, P equals IV or VI, voltage times current. Let's stick with VI. Okay, V equals IR, and P equals V times I. So for a resistor, we can combine both of these equations together, and we can generate two more equations. Okay, so we combine these two equations together, and we can generate two more equations. Power in terms of current and resistance, it would be I square times R. And in terms of voltage, it would be V square divided by R. Okay. V square divided by R. Again, remember, all of circuit analysis is based on just these three laws. We have Ohm's law, we have KCL, and we have KVL. Everything else is derived from here. And so the only other equation is the power equation. And the power equation combined with Ohm's law, we can have these two equations derived from there. So these are like shortcuts. If you have resistance and you have current, you don't need to find voltage in order to find power. You can simply use I squared times R. If you have voltage and you have resistance, you don't need to find current from Ohm's law. We can skip that step and directly apply V square over R. Make sense? Okay. I'm assuming that was also there in your physics classes, perhaps. Okay. Okay. So here, I think there's a spelling error in there. There should be a O Joule's law of heating. So if you have a resistive device, like an electric heater, what we talked about, right? The heat that is generated, delta H right here, can be written as I squared times R times the total time that was used. So times delta T. And that's the total. And now let's move to our examples. All right, so in this example, we have a heater that is rated for 100 watts, operates at 12 volts. Okay. I think you can read through here just about 12 volts, 100 watts, and there's something else to the right. I don't know what that is. All right, so 12 volt and 100 watt. Let's say it is a heater device. Okay. The answer is already provided, but let's walk through the steps, the logical steps, as well as the equations. So what do we have? We have acquire or extract as much information as we can from the given statement. We have voltage, 12 volts, so extract information. And we have power, P equals 100 watts. So you have two equations, V equals IR and P equals VI. You have two of the four quantities. What we don't have is current, and also, let me write down there. I is unknown, and so is R. And again, always think in terms of what is known, meaning provided in the problem statement. It could be in the figure or the circuit diagram. It could be in the problem statement itself, or if there's a graph or a chart, information could be on the graph or chart also. So extract as much information as you can, write it down. Here we know the voltage is 12 volts. We know the power is 100 watts. What are the unknowns? Current I and resistance R. We have our two equations, P equals VI and V equals IR. Apply them in any form you want, any order you want, and we should be able to find both of them, I and R. And that is what is shown here. Okay. You could find the resistance directly from V and P. We just saw that. P equals V squared over R. And of course, you can find I simply from P equals VI. All right, let's take a pause to think over that. Let me know if you have any questions. Make sense? Right? All right. Now, how many of you have looked at the tech specs of a of your smartphone or your tablet? Have you ever purchased a portable battery pack? Tech specs of the battery pack will always include the capacity. Capacity, more often than not, or actually not more often than not, pretty much always stated in terms of AH, ampere hours. Ampere hours and a specific voltage. Okay, so it's always stated in ampere hours and a specific voltage. So thinking logically and intuitively, what do you think it means? Anyone? That is correct. How many amps it can supply for an hour at that specific voltage. So you have voltage V, you have current I. So you have volts, you have amps, and you have hour, which is time. So if you check the actual tech specs of your phones or your mobile devices, it will tell you the voltage it runs at. Probably 3.7 volts for most devices. And then most phones have a battery that is around 4,000 or 5,000 milliampere hours, mAh. So it will be, I want to say, phones and tablets, or modern day phones and tablets, will be milliampere hours, mAh. Okay, mAh. The reason we use milli is because most devices, the current would be in the order of milliamps. So it makes it easier. Okay. So it'll be like 5,000 milliampere hours. 5,000 milliampere hours would simply mean 5 ampere hours. Okay. Now, why is this important? Well, it basically would tell us how long we can use our devices at that specific voltage and how much we consume. Okay. So if we know the current draw from the device and we know the voltage it operates on, then we can predict how long the device will last. So for instance, if you have a 1,000 milliampere hour device running at 5 volts, and it's drawing a current of 10 milliamps. How long would it last? When they send you all back to elementary school? The 100 is one response. Anyone else? 50 is another response. mAh, or just AH, ampere hours, right? So T would simply be 1,000 mAh divided by 10 mA gives us how much? I should write the full form. Okay. Obviously, smartphones and tablets are going to use a higher draw of current. It's not just 10 milliamps would be very small in that case. Like a smartwatch, perhaps, might last longer than that. But again, the smartwatch battery is not as big as 1,000 milliampere hours. Smartwatch batteries are around 300 or 400, very small. Typical smartphone batteries would be in the 4 and 5,000 range. Okay. If you buy a portable battery pack, its specifications will definitely include the capacity right at the top. Nowadays, solar battery packs are very popular for use as like portable devices and in place of like, fossil fuel generators. And so actually, it doesn't even matter whether it's powered by solar or not. Just a battery pack. You can buy battery packs with built-in inverters. They've become very popular now. Okay. So people who go camping, or if they just want like a battery backup at home, they simply buy these battery packs, inverters, comes with AC power outlets. You can buy them in a variety of capacity and sizes. And so it'll, right in the tech spec at the top, it'll tell you the first line will be like a 300-watt battery capacity or a 300-watt inverter. But then the second spec, which is the most important, it tells you the battery capacity, which would be 300 mAh or 3000 mAh. Okay. And there are huge battery packs that you can mount permanently or fix permanently inside your residences and buildings. So assuming, or not, let's not assume, but how many of you are aware of the product called Tesla Powerwall? Right? A Tesla Powerwall is simply a battery with an inverter that's mounted on the wall, like a flat rectangle almost. Okay, so if you look at the tech specs of this battery, the Tesla Powerwall, it shows, I think it's 13,000 watt hours or something, if I'm not mistaken. And let's say it's 10,000. Yeah, let's say it's 10,000. So it's 10,000 watt hours. Okay, so it's mounted on the wall. Depending on the voltage that's required to run it, it can power your homes for hours. Okay, and you can buy these battery packs along with the inverters on the market. Doesn't cost a lot. It's about $1,600. You can get like a 3,000 ampere hour capacity. Ampere hours, by the way, have another significance. In everyday life, we talk about units of electricity. Are you familiar with the term? So 1 unit of electrical power is equal to 1 kilowatt hour. If you consume 1,000 watts for 1 hour, you're using up 1 unit of electricity. If you look at the power bill, assuming you are renting a place and you're sharing or not sharing or whatever, it'll tell you how many units of energy you consumed per month. And that unit is 1 kilowatt hour. So it's consuming 1,000 watts of electrical power for 1 hour. Okay, so that's 1 unit of electrical energy. All right, any questions? Okay, so coming back to this example here, let's say a typical vehicle battery is 70 ampere hours. Rated at 12 volts. A car's electrical system runs at 12 volts. So what is the total capacity? Well, 70 ampere hours multiplied by the voltage gives you the total capacity. You take T out from it. So 12 times 70 gives you 840. So you have 840 watt hours. 840 watt hours divided by the requirement of this device, which is 100. It tells you how long that battery would power your device. Okay. Again, it's voltage, it's current, it's time. So if you have a battery capacity of a certain watt hours, you have the voltage, you can calculate the current, or the requirement for the device, you can calculate how long it's going to last. So the question here is, if you have a battery with these specs, 12 volts and 70 ampere hours, then your total capacity is 12 times 70. And if your available energy is 12 times 70, which is 840, right? 840. Then how long will your device last? The device lasts, because it requires 100 watts, there will be 840 divided by 100, gives you the time. Let's take a pause. Let me know if you have any questions. Yes. Yes. Yeah. Kilo. So the question is about the units. The kilo is simply the unit prefix for 1,000. That's all it is. So 840 watt hours would be 0.84 kilowatt hours, or 0.84 units of electricity. And then, of course, if you want to calculate the power, simply V square over R. And if it's running at 5 volts, or if a device running at 5 volts, we'll pull in 17.3 watts. Okay. It's the same equations. The questions are different. Once you extract information, you find the knowns, or you write down the list of known values, and then you write down the list of unknown values, and then you just apply the equations in any order that you want. Okay. That's how we approach these problems. All right, let's see. That's that one, and that's spice verification. Okay. All right, so how much power can this heater deliver if it is supplied by a very, very long cable? The ideal cable, the length does not matter because the resistance is always 0. But in real life, we must take the resistance into account. So if the resistance of this cable is 50 milliohms, and you have two cables, one for the hot wire, the other one for the return wire, or plus and minus. Each one of them is 50 ohms or 50 milliohms. You have to factor that in your calculations. So the way we calculate this is by applying KVL. So from KVL, I can write 12 volts is equal to the voltage across that first resistance plus the voltage across the load plus the voltage across the second resistance, VR2. Okay, 12 volts is the source, so that must be divided across the 3 resistors. Now, current for a source goes from minus to plus. So current goes in this direction, upwards direction. It has nowhere else to go except make a right turn. And so it enters the resistance from the left. So this is plus, this is minus. The current goes down. So this is plus, this is minus. Enters the bottom resistor from the right. So that's plus, and this is minus. As the current passes through, it drops a voltage across each resistance. Point of entry of the current is always plus for a resistor. So if I apply KVL around this loop, I can take all the voltages together. I can do minus 12 plus VR1 plus V load plus VR2 is equal to 0. Or I can simply write 12 volts is equal to the 3 voltages, or the sum of 3 voltages. Apply KVL in the manner that you are accustomed to. Okay. You've all studied KVL. You've done it in physics. You might have done it before also. So if you're used to a particular method or a way to apply KVL, just stick with that. Okay, write out your KVL equation. Then we apply Ohm's law. And when we apply Ohm's law, we can write VR1 is equal to the current I, because it's V equals IR. So I times R1 plus I times R load plus I times R2. That's how we obtain that equation. I is common, so you can take it outside, and it simply becomes R1 plus R2 plus R load, and you have this equation. And you can calculate the total current that is flowing through that circuit. Okay. The power for the load is then simply I squared times R. Which is what we have in this equation. I squared times R. Okay. Let's take a pause, think over that. Let me know if you have any questions. Any questions? Okay. All right, then let's go to SPICE verification. Let's see, ammeter, no. All right, SPICE. How many of you are familiar with SPICE? Not the spices we use in our cooking. The spices are a little different. All right, SPICE was a program that was invented or created at UC Berkeley in the 1970s. Okay, it stands for Simulation Program with Integrated Circuit Emphasis. All right, it was created again. It was created as a derivative of a U.S. government program called CANCER. Yeah, I know. And CANCER stood for Computer Analysis of Non-Linear Circuits Excluding Radiation. All right. So it was a derivation of that. But as with any programs there, this was right after World War II. Governments were sinking a lot of money into industrialization and then development of computers, right? So the 50s and the 60s and the 70s were all about that. So this program, computer analysis, is at a time when computers are like brand new, right? Computers occupy the size, like machines that occupy the size of this room. And so because it's government funded, it's government provided, it's restricted. Well, the professor at the time, his name was Peterson, and Dr. Peterson, what he wanted to do was he wanted to make this program open source, so it was available to everyone. Well, if you want to do that, then you have to rewrite the program, you have to rewrite the code. And so he had a student of his who was already working on this. He rewrote that program. Again, think about this, 1970s, right? Late 60s and 70s. Completely rewrote the program and they put it in the public domain. Okay, if you visit the Berkeley campus, outside one of their buildings is a plaque that's devoted to Dr. Peterson and the development of SPICE. Okay, so again, historical fact if you want to. SPICE is based on nodal analysis. Okay, so it's nothing but all simulation programs, and SPICE included, are nothing but calculators. They have a bunch of equations in there. You feed input to the calculator, It runs through its calculations and it gives out an output value. And so it still, to this day, SPICE is the gold standard in circuit simulation. Okay, all variations of SPICE that are available today are based on that original program. There is a program that is available for free, and it comes from Linear Technologies. And their version of SPICE is known as LT SPICE. So one of the homework questions is you need to download or search for this program. It's not as if it's hidden. Just go online to the internet and you type LT SPICE and it'll come up with a download link. It's a freely available download. You download this program. It's a graphical interface program, so that in some ways it is better, because in SPICE, it is like it's character based. Okay, so you're typing it up. You're typing it up and you're saying, okay, node 1, you're connecting terminal 1 of the resistor, terminal 2 of the resistor, and you have to type it up. And there are advantages to doing so, because you can create each and every aspect of your circuit when you type it up. If you're using this graphical interface, you're limited to the components that are included with LT SPICE. Okay, but as a starting point, this is a really great tool. You download it and install it on your laptops. It works on both Mac as well as Windows. But the program is not as intuitive in the Mac because it does not have a menu. Everything must be done with like a right click, which again, Mac does not have a right click, not unless you enable the 2-finger tap. So it's a little limited in there, but in Windows, it works on both Windows and Mac. All right. So you'll create this program in there. And what we have to do is you have to select resistors, you place the resistors. And once you place the resistors, you have the source in there. You need to add ground. Circuits will not simulate without a ground. That is always been true going back to the first version of SPICE. Circuit needs a ground reference. The ground reference is placed. You enter the values of the resistors, and then you run a simulation. You click on dcanalysis.op. You click OK, and it will place this somewhere next to your circuit. Okay, and that's the indicator for the software to run through its calculation, run through its simulation. Run through its simulation, it'll provide you some answers. Okay. And so you run through your simulation, it'll get your answers. One thing I want to point out, again, this is not a sentient being. This is not AI. So it needs to be told what it needs to do. Resistors do not have any polarity. But in LT SPICE, when you place a resistor, it does have polarity. So when you first click on resistors in LT SPICE, it's going to appear as a resistor like this. And this resistor has a plus at the top and a minus at the bottom. When you create your circuit and you're placing a resistor, the first position is like this. Then you press Control R, the resistor is rotated. Now it's flat, but it rotates like this. So it's plus here and it's minus here. Then you press Control R again. Now the resistor is like this. You press Control R again. And finally, you will get this. Why is this important? Because if you create this circuit, as I showed on the previous page, the top resistor has a plus on the left. The bottom one has a plus on the right. If you do not lay out your resistors correctly with like this, your answer, your magnitude will be correct, but your answer will be incorrect. Okay? Your equations will not balance out. So you have to keep this in mind. So you rotate. And rotation is done at CTRL plus R. The entire program can be run with keyboard shortcuts. Okay, and there's a huge worldwide community that is devoted, not forums where people try to identify the solutions, identify the problems and the solutions in Spice as well as LT Spice. Okay, you will see that on the internet when you do your search. All right, let's stop here today. There's one more slide, but we'll tackle that on Friday and then again move forward from this point on. Right, so I'll see you all on Friday.